Okay, we are ready to go. So our fourth and our final session on faith and science. And once again, I have prepared another one to begin with. In the name of the Father, and the Son, and the Holy Spirit. Amen. Our God and our Father, we thank you, God, for your infinite wisdom, the unfathomable depth of your knowledge, and your boundless creativity. Lord, we pray that as our days, weeks, months, and years unfold before us, that your Holy Spirit instills in your people an eagerness to learn about your creation and share their findings with a watching world. Lord, we ask that men and women whom you have gifted with a curious mind, a steady hand, and an unwavering faith become leaders in our scientific enterprise. May the people you have made remember, our help is in the name of the Lord, the maker of heaven and earth. Amen. Okay. In this last session, I'm going to bring a couple of other topics to a close. I'm going to add a little bit to both topics because I think they both deserve a little bit more. The first one is a continuation of the thoughts that we had last week when I showed that picture of the Apollo 8 mission, and I picked those four elements to talk about their wonders. That was kind of a poetic choice on my part, but I left out two things that are actually really important, and today I'm going to pick those up. And those are carbon and oxygen. I'm going to do those. The second thing I'm going to pick up is what we said about the Earth and its amazing home that it is for us. And there's a lot of information that's not known that I think you'd be really interested in hearing that will add to your knowledge of how amazing our home on Earth is. And that will complete that story. I won't take a great deal of time on that, but I'll do both those topics. And then I'll go into two other very recent topics relative to everything else that have a particularly strong impact or should in the near future. And that is the Shroud of Turin and near-death experiences. Both only for scientific reasons. I'm not going to get anything but the scientific aspects of both of those. Ready to go? Okay, let's go. A couple of sessions ago, I put up this chart. Remember this? We talked about how all the stars create all of the elements, and we said these are the elements in the human body. If you look at it, you see that our bodies are made up primarily, over 96% of our bodies is hydrogen, carbon, nitrogen, and oxygen. There's something very fitting in that those are the elements that almost every star produces at the end of its life. Despite all the other ways in which elements are weighed, it's as if the universe created that as it began, knowing that life would be the outcome. The other ones are important, but those are the basic ones. Just to go back and review, because I remember I showed this very briefly, all of the elements, you may recall, are made by the stars. And they have life cycles, and those life cycles have played out many times over the universe. The life cycles are very different. Some are very, very short, only a couple of million years or so. Others are like our sun, are 10 billion year stars. Some will last theoretically trillions of years. And they all do different things at the end of their lifestyle to produce the elements. But I just wanted you to see that because we'll be talking about some of these. The two at the very top in the brown, the Big Bang, that from the very beginning, hydrogen and helium. After that, stars like our sun produce the next ones, which is labeled stellar nucleosis. Our sun produces, or will produce, it doesn't, not right now, it's in the main sequence. All it's doing is making helium out of hydrogen now, and that makes life good for us. But when it gets really old, it'll make it in nitrogen. it's not a real big star. It's actually called a white dwarf, a G star. But some of the bigger ones will make the other brown ones that you see. All those including magnesium, sodium, phosphorus, sulfur, nickel, chromium, all those will get made by other ones. And then other stars which are rarer and rarer events, make the rarer and rarer elements, take rarer and rarer conditions to do that, such as the. And the things that I'm not even going to get into what neutron stars do is just impossible to even talk about almost. So that's how everything gets here. But the point I want to make is that these elements out there in the universe experience two kinds of conditions. One, when they're being made in the stars, and the other, when their stars blow up or die. They blow up in different ways, some in a fantastic fashion, some more gently, like our sun will gently become a red giant and just kind of go poof. But the conditions couldn't be more different. In the stars where they're formed, they exist in tens of millions of degrees. The only other environment these elements ever see is when they're in space. Our sun is about 27 million in its core. Some other stars that are bigger are hotter, some are cooler. It's only about 5,000 or 6,000 degrees on the surface when all that energy radiates out slowly, layer by layer by layer, and then gets to be that kind of energy that you and I see with, starting off with the very high intensity stuff and giving us finally the other stuff. But once all these stars go through their life cycle, all their particles go off into space. And space couldn't be more different than the stars. Okay, here we go. 99.999999999% of space, of the universe, is empty space. The rest is stars, and an unbelievably tiny fraction is places like planets, exoplanets or the Earth or things like that. So that's the environment that the elements experience. Here on Earth, they are in an environment that is just utterly uncharacteristic of the universe. And that's what we're going to talk about today when we talk about carbon and oxygen. In this environment, those two key elements to life are experiencing this incredibly tiny range of temperature and pressure. Our sun, I told you, was 27 million degrees Fahrenheit. The pressure is even more startling. The pressure in the core of the sun where it makes the elements is 340 billion times greater than atmospheric pressure here. It's just almost inconceivable how different the universe is. So let's go on to talk about carbon. Carbon is what we think of as our life. We talk about carbon-based life. It's so fundamental to life, and it's also so unusual. It has a property that no other elements have that makes it so fit. I'll have to describe this to you because the name of the property hardly makes sense. The name of the property is metastability. Metastability. It's a word that expresses two opposite ideas. Carbon actually has the properties in our conditions here on Earth, the conditions of lability, which is the ability to change and do lots of different things. Lots of different chemical compounds can be made with carbon. Hundreds of thousands of chemical compounds can be made with carbon. It's the most labile, L-I-B-I-L, the element with the most lability of any lability. But it's also got great stability. In chemical terms, those are opposites. Lability means the ability to enter chemical reactions. Stability means the ability to not be chemically transformed. And yet carbon has both of those elements, and it's called metastability. So it's a molecule that can liberate a great deal of free energy through a transformation, which is characteristic of very reactive chemicals, but it's also one that can remain stable for a very long time. But again, this is only true in a very small temperature range. That temperature range, when you consider all these properties, is from about minus 20 degrees centigrade to about plus 120 degrees centigrade. Now, if you're not familiar with centigrade, minus 20 C is a little below zero. Carbon is been called the universal chemical constructor kit. It can make so many different materials. Oh, there it is. Good, we got it. It's got the ability to make so many different materials. Here's what they are. Some of you, let me just ask a show of hands. How many chemistry? Oh, good. Okay. So this isn't going to. If you've had a little bit of college chemistry, you took organic chemistry, and you see some of those things. These are just some of the things that carbon can make. In this diagram, if you're looking at it, R just stands for any kind of a carbon backbone, and all those things in circles are all the different chemical groups that can be appended to any kind of a carbon backbone to make any kind of a compound that you want. And these are so critical. The fact that it can make so many, as I said, hundreds of thousands of different materials. In our bodies, we use them all. Amino acids, it's the one labeled amine there. Makes the proteins. That's what's all the structure, everything from our skin to our hair, eyes, everything. The carbohydrates that we have for energy, but also for brain function. All the lipids and the sugars. You know, we tend to think badly when we talk about fats and sugars, but they're absolutely essential. In fact, the lipids, people don't understand how vital a part the lipids are of our very construction. Because, as you know, we're about 2/3 water, right? That's how everything works. But with all the water, you got to keep all those water-bearing cells apart. And the thing that keeps them apart is something that doesn't like water, which is lipids. It's these phospholipids, fatty acids and fats, that our body uses to construct the cell membrane, which a lot of people don't realize is intricately designed. A cell has to do so much, and yet it has to interact with the rest of the organism intimately, and the membrane regulates that beautifully and wonderfully. So that's extremely important. Aldehydes are important in energy production when you're under stress. Ketones, likewise, and alcohols, again, are very involved in cell membranes, and especially in enzyme and hormone production. All of this is so very important. We are an amazing collection of carbon macromolecules and all other kinds of carbon molecules. We are carbon-based life in every way. And the amazing thing about gives carbon this capability to be so flexible is the way that it is put together. These carbon molecules are put together by, again, if you've had chemistry in your high school, you've heard of the way chemicals bond, right? And you've heard of strong bonds like covalent bonds, and they're strong bonds. That's what happens in forming all these carbon compounds. The covalent bonds are the ones that exist. In this case, this is a chain of amino acids. So each one of those little rings is an amino acid of several elements. So the strong bonds, the covalent bonds, would be both within the amino acids and between them. All that's the strong stuff that holds that together. But then there's several other ways that, in addition to structuring it, it gets shape. And shape is critically important to everything that happens. And that's done by these secondary bonds. Again, if you had high school chemistry, hydrogen bonds, van der Waals forces, London bonds, things like that are weak bonds that occur between the molecules, whereas the strong bonds are within the molecule. Carbon does both with aplomb. And so you get structures, especially like proteins, where you first get one layer of weak bonds that gives a helix or a sheet or something like that, and then another layer where it all coils together and forms a three-dimensional structure, and then it even goes on, and you get different types of different structures which unite together and form very complex structures. And we're going to talk about one in a little bit when we talk about oxygen and the role that hemoglobin plays when we talk about that. So this incredible flexibility of carbon that no other element has. There's been talk, people who do sci-fi talk about what other kind of life could there be out in the universe? And there's been speculation it could be silicon-based. Ever hear that? That became very popular. It's ridiculous. Silicon, it mimics just a few of carbon's properties, and nothing after that even comes close to silicon. It's carbon or it's nothing. One thing we know is if there's any life in the universe, it is carbon-based. It just isn't even possible to go anywhere else with it. And one more thing about carbon's metastability. It has metastability in two ways. There's first a metastability of the structure of the compound, the metastability of it holding together. And that's maybe the one that comes to mind first. But there's another kind of metastability, and that's the metastability of shape, because shape is so important. Well, it turns out that the carbon compounds are stable in this minus 20 to plus 120 degree range, which is interesting because that's like what? Like Earth, right? It's like our biosphere is within that range. That's the only place where you get this metastability of the strong bonds. But the metastability of the weak bonds, the ones that control the shape, is even narrower than that. The weak bonds are only stable up to about 50 degrees centigrade, about 120 to 130 degrees Fahrenheit. After that, it doesn't work. And below zero, below the freezing point of water, nothing works. So only in that narrow range that we all actually experience can these carbon molecules retain their shape. No other conditions, but what's right here on Earth. It's a litany of properties that is amazing for carbon. Okay, let's move on to oxygen. Oxygen is like carbon's partner in life. Carbon is what we're made of, but oxygen is what gives all that carbon life. Without oxygen, we couldn't do anything. It's the near universal activator of carbon-based life. Again, for those of you who did your chemistry, the word oxidation is known to you, right? Oxidation just means something's reacting with oxygen. It's got a name because it's so common. Many things react with oxygen. Well, it turns out that oxygen releases more energy in whatever it reacts with than any other chemical except one, and that's fluorine, which is very close to oxygen in the periodic table. But fluorine's useless because all it produces is noxious materials that can't support life. So oxygen is the element that releases energy contained in carbon, which is next to hydrogen and rare boron, the element that contains the most energy. In other words, life is based on carbon, which is energy rich, and oxygen, which safely releases more energy from what it reacts with than any other chemical. Do you see the pairing? How well it works together. Those are the properties. And again, the properties of oxygen are again tuned to the conditions that we have here on Earth. In our world, the oxygen that we have in our atmosphere doesn't exist as elemental oxygen. Again, those of you who took chemistry know it's O2, right? And the word for that is dioxygen. It's not atoms of oxygen. It's molecules of oxygen, each containing 2 atoms. But oxygen has a property which is extremely unusual too. And if it didn't have this property, because it's so reactive and has such an ability to release energy from what it reacts with, if it didn't have this property that I'm going to tell you about, without it, in our atmosphere, which is 21% oxygen, and the rest mostly nitrogen and some other inert gases, if it didn't have this property, what would happen is that almost everything would quickly react with air, everything that's here, forming water, carbon dioxide, and nitrogen. There just wouldn't be any way to have life because oxygen would just react with everything so quickly because it needs that reaction property, but it releases the energy, but we couldn't control it. But the reaction, as we all know, doesn't happen that way. We can walk around safely, and we don't self-combust. It doesn't happen. This property in dioxygen is called paramagnetism. And it's, again, for those of you that took the chemistry, if you remember how elements share their electrons and form bonds, remember that in your chemistry? And you were taught in chemistry that oxygen, which has 6 electrons in its outer shell, shares two electrons with another oxygen atom, and the 2 of them form a bond. Well, that's not exactly what happens. It's true that they share the electrons, but not in the way that you were taught. They only share one of the electrons in the way you were taught, and the other one not in the way you were taught. And as a result, oxygen has a property because the electrons are not fully shared, and the molecule oxygen is not really neutral. You're going to be surprised to learn something. Watch what happens in this little video when some liquid nitrogen is poured between the north and south poles of a large magnet. Then oxygen is poured between the magnet, okay? Just watch. First, nitrogen. Obviously, those are both liquid. Those are supercooled nitrogen and supercooled oxygen. And you saw that oxygen is magnetic. Surprising, huh? Wouldn't think of it, but it's critical. It's because of what are called these 2 unpaired electrons that give it this magnetic character. They're like literally sitting out there and giving it the ability to be magnetized instead of being tucked in the bond. That's what happens to do it. But that's a property of oxygen, but all the organic compounds of carbon, all of them have just paired electrons. So none of the carbon compounds have this feature, whereas oxygen does have this feature. And that's the reason that the compounds with carbon, made of carbon, any one of them, don't readily react with oxygen, because compounds with paired electrons don't want to react with compounds with these unpaired electrons. So it keeps it from happening. But again, this is temperature dependent. This property of oxygen doesn't exist beyond about, again, 50 degrees centigrade, 120 degrees Fahrenheit. Above that, it doesn't happen. It's only attenuated, again, at temperatures that we have on Earth. Another amazing property. So with that property, that's reason why at our temperatures that we just don't have instantaneous forest fires. But it's been shown that in our atmosphere, which is 21% oxygen if it were just a little higher at 25% oxygen, Earth would be unlivable. There'd be so many forest fires, so powerful you wouldn't be able to put them out. Just at that much more. It's that finely balanced. Okay, so that's the fundamental characteristic of oxygen. You'll see more about this as we go on, because let's carry the oxygen story with regard to us a step forward. For us, what's got to happen is we are very energetic creatures. You know, we're not mollusks sitting at the bottom of the sea, or a snail, or just a simple animal not doing much. We're energetic creatures. We've got tons and tons of cells that need lots and lots of energy. So we got to get the energy that oxygen can deliver to our carbon-based life cells and give them the energy to do all the things they do. We got to get it there. How does oxygen manage to get there and do this? This is the other part of the story. First of all, we breathe it in our lungs. We get it from the air, and from there we got to get it into our system, which is water-based, right? So oxygen's got to be soluble in the liquid system of our bodies, which is water, right? It turns out the solubility of oxygen in water is about 0.6% by volume. So only a little bit of it goes in. So it's like 6 tenths of a part for 100 parts of oxygen solubility. It's not a lot. But it turns out if it was any higher, it would actually be deadly, because oxygen and water actually is in equilibrium with some radicals called superoxide and dioxygen, which are radicals which are very reactive. And in fact, it even forms hydrogen peroxide, which I think everybody knows is a material that's dangerous. So the solubility couldn't be any higher. So what there has to be is a way to get that oxygen to our bodies despite the low solubility of oxygen in water. So how do we do that? How do you get all that oxygen, that huge amount, into our cells? By the way, if you're just sitting or sleeping, not moving any energy, you're consuming pure oxygen at the rate of about 8 ounces a minute. Not air, pure oxygen. Multiply that by 5 for the air. Okay? That's how much oxygen you'd have to consume and feed your body. If you get up and walk around or run, it increases several-fold how much oxygen you need. So what we need is a transport system that's equally amazing. And this is carrying the story all the way because I want to carry it all the way to us. So how do we get all that oxygen to our cells? And how do we not only transport a lot of oxygen, but how does the transport mechanism let it go and get it into our cells after it carries it? It's got to do both things. And that's where something really remarkable happens. And that's the next subject. This is hemoglobin. Anybody in the medical field here? Okay, I'm probably going to embarrass myself because I'm going to try and talk about hemoglobin. And that's not me, but I'm going to do my best, okay? But hemoglobin fascinates me as to how well it does this. Because first of all, hemoglobin is again, one of those amazingly complex structures. Remember those things about the proteins and the folding and everything? There you see it in hemoglobin. And it's not just one, but there's, I think, 4 different amino acids that are involved in making the structure, plus a complex that's called heme. The protein's called globin, the complex is called heme. And the heme interacts with both the proteins in the amino acid structure of the proteins, and also it complexes with the iron as well. And it's this construction of the complex, the physical construction, that makes it so amazing. And what it does is it creates the ability to transport a lot of oxygen. Hemoglobin contains about 50 times the amount of blood that would be soluble in the cytoplasm of our cells. In other words, in our liquid system. So we can carry a huge amount of oxygen. And it's this amazing set of properties that make this possible. That complex that you could see is very, very shape dependent. And what happens is it's constructed out of proteins, some of which are hydrophobic and some of which are hydrophilic. Now, hydrophilic means it likes water. Hydrophobic means it tends to reject water. It's constructed so the hydrophilic ones are on the outside and the hydrophobic ones are on the inside, where the heme is and where the iron, which is so critical, is attached to. And remember that magnet now. There's iron in there, okay? That's going to latch onto some of that paramagnetic oxygen in an area where it's hydrophobic and the oxygen can go, and it can stay there and get carried. And so it takes this from the lungs and carries it through the blood system with these complexes, and by the time it gets to the cells, I don't understand this, how it happens, but by the time it gets to all the way in the arterial system and gets all the way down into the tissues, in this fine capillary system, it spreads out and releases the oxygen. It releases oxygen, which now either has no paramagnetic character or much, much less. In other words, it's modified the oxygen and then delivered it in a reactive form where it can be useful in the cells, and it diffuses into the cell as the source of all of our energy that will come. And when it gets in there, I know this is a little carrying the story all the way, but I think it deserves to be carried because it completes the story. The oxygen then diffuses into the cell, and in every one of our roughly 30 trillion cells, there are hundreds or thousands of little organelles called mitochondria, which basically are batteries that take that oxygen and through a very, very complex system, process the oxygen and produce something called ATP, adenosine triphosphate, which is a way in which the oxygen is taken and made available as a form of energy for all the things in the cell that require energy. In our cells are hundreds of thousands or even millions of little proteins and motors that are moving and carrying things and doing stuff that need energy. And every single step along the way, they've got to get energy, and ATP from the oxygen gives them the energy. And then, of course, all the waste products go back out again. The thought of what goes on in a human cell is absolutely mind-boggling, the amount of activity that's there, and the way that we get there, and the way that this process happens. And I'm going to drop it here. If we really had a lot of time, we could talk about what happens with carbon, zinc, manganese, and molybdenum, and everything. The point is the design of these elements is so specific, and the tasks are so complementary in their design. It's amazing. Just to read about hemoglobin blows my mind at how it works, and there are many other subjects too. Okay, let's go on then from there. I said I was going to pick up the topic of the rare earth as well and go back to that. I got a diagram here I want to show you because I'm going to move off this quickly. I know everybody's heard about the habitable zone in our solar system, which is you could be so close to the sun but not too far from the sun, and there's only a zone you can live in. This diagram is way out of scale. Don't worry about that. The only thing I want to show you is how close all the terrestrial planets are here, and the fact that this is where life is as we know. It turns out, but everything else is off scale. This scale here is true, okay? Just the zone. I just want to show you how far the scale is. An astronomical unit from the sun. That's just by definition. And all the other ones are the numbers that you see there. But what you probably never hear about is habitability zone in our galaxy. That's something that very few people know about. But that's a factor too. There's a place in the galaxy where you can live, and a lot of places where you can't live. And if you look at this diagram, I don't know if you can see it, but right here, with the lines radiating about it, that's us, right there. And the green area is roughly an indication of the habitable zone. It's a very, very rough indication, and I'll tell you what some of the qualifiers are. The reason that's the habitable zone of a galaxy is important is you don't want to be too close to the center, just like you don't want to be close to the sun. Different reasons, though, because in the center of the galaxy, there's just so much activity. There's a lot of gamma rays, X-rays, cosmic rays. There's a black hole in the middle, too. Everybody knows what that is. You wouldn't get near that. And so close into the center, life isn't possible, close to the center of the galaxy. Also, there'd be enormous gravitational forces. And we've got something in our solar system called an Oort cloud, O-O-R-T. Ever hear of that? Way out beyond the orbits of the far planets is a whole bunch of small bodies, just rocky things in different sizes, shapes. Pluto got demoted, remember, a few years ago. It's out there too. And every once in a while, these bodies, and there are thousands and thousands of them, and they're way, way out far from the sun. But they have weird orbits, and every once in a while they come in close, and sometimes they get kicked in close. And when they come by, we call them a comet. And everybody knows what killed the dinosaurs, right? 65 million years ago, when a comet hit the Gulf of Mexico, and all the dinosaurs died. So if you got too close to the center of the galaxies, the Oort cloud would get very disturbed, and oh my Lord, we'd have comets, and we wouldn't want that. Too many of them. Also, you can't get too far from the center of the galaxy because the star histories are dependent upon where you are in the galaxy. You get certain types of stars and certain types of histories. And one thing we need to have Earth is we got to have the right collection of elements. We got to have all the elements that we need for life. And this is called, in cosmological terms, it's called metallicity. Metals is just a cosmological term for any element beyond helium. It's just a term. It doesn't mean much. It doesn't mean metal in a common sense. But this term metallicity tells you how much of these elements you have. And to have everything we need enough, but not too many. If we didn't have enough, we couldn't have life. If we had too many high metal, we had too much metallicity, we'd have big planets close to the sun. And those big planets would gravitationally, at some point, disrupt Earth or just simply gravitationally draw it and destroy it. So we're in a sweet spot there. It's a very sweet spot. And the other thing you'll probably notice, if you look carefully, is that point where the sun is, it's not in a spot that's in one of the arms of the galaxy. Notice that? It's in kind of a black void area. There are these galactic arms. There's called a Perseus arm and a Sagittarius arm close in. We're between them, but we're in a space which is kind of like blank, right? There's not a lot of stars near us. Is that important? Yeah, it's really important. Because if we were in an area, in one of those arms, those are the areas, you've probably seen these photographs, where you see these clouds of dust and stars are being formed. It's beautiful. But again, there's a lot of activity. There's supernova, there's cosmic rays, there's quasars. There's all kinds of things that would keep Earth from having this long, long cycle for life to evolve. So we avoid that intense radiation and all those things. But the other thing about being where we are, not in a galactic arm, can anybody think of another reason to not be there? Huh? Exactly. Yeah. We wouldn't have a night sky. How would it be if we had life with no night? It was just stars all the time. It just wouldn't be the same. We wouldn't have the ability to explore. And finally, the other thing about it, which you can't see on the graph, is that the nature of the galactic rotation of our solar system around the galaxy has got two other characteristics that are wonderful. And they're both unusual. One is that the rotation rate of our solar system around the galaxy is synchronous with the arms of the galaxy that we're near. So we're not going to cross them. We're going to stay where we are and keep us there. And the other characteristic is that the orbit of our solar system is very, very close to circular, which keeps us again in the same relative position. In other words, it's very, very stable. So we got all those things going there. All of this has become clearer and clearer in more recent years. Taking all this together, I told you over the last several decades, ideas have percolated a lot. Oh, I forgot I had this one here. Yeah, you can see it better here. Sorry, I didn't put this one up. You can see our sun right there more clearly in that galactic void right there between the Perseus and Sagittarius arms. Okay, let's go on a little bit more. Let me tell you about the ideas that have percolated around for the last 3 generations. There was a famous physicist, Nobel laureate by the name of Enrico Fermi, who just over lunch one day threw out this one idea when everybody was talking about life, in the probability of life in the universe, in the galaxy in particular. And the view was that life was very, very common at the time. Much less of this was talked about and known. And Fermi once, just at lunch, said, well, where are they? Why don't we see them? And because he was Fermi and he was very famous, it got taken up. And it became known as Fermi's paradox. Okay, there's lots and lots of life, we think, out in our galaxy. Why isn't there any sign of them? And ideas circulated and circulated. In 1961, an astronomer by the name of Frank Drake came up with something known as the Drake equation, when he made just sort of an estimate of the likelihood of coming in contact with some other life in the galaxy. And this Drake equation was just a series of factors, which I think you can see, which you could just multiply them and just come up with what's the odds of it. So you just multiply one factor by another factor by another factor, each of which is very slight, and multiply that by the number of stars and the number of likely planets with billions and billions of stars, and then come up with, well, how many civilizations do you think we could communicate with? This is 1960s. The thought at the time was thousands and thousands of them are probably out there in the Milky Way galaxy. That was the thought. In 1984, an organization called SETI was started. SETI is the Search for Extraterrestrial Intelligence. E.T., right? Come home. And it was private. It was not a government-sponsored thing. But our friend Carl in big time, believing again, still in the 1980s, that we could look for and we would start finding extraterrestrials. And the hope was high that we would find them. And SETI's been operating for 40 years and been putting in better and better equipment and more money and getting more and more grants. And so far, SETI has done nothing. No contact. Not even a whimper has happened. In recent years, as I said, we've learned more and more and more. The academic scientific community hasn't been very interested in this. This is an area where other communities outside the mainstream have done some good science. And I'm going to play a short video here to end this session and to tell you what we have learned in the last generation that is changing all the thinking that went before. Here's it.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, that it has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that it has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities. And that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillion. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
There was that last thing you heard him say, the conclusion we're rare, that was formulated years ago into what was called the rare Earth hypothesis. In other words, the antithesis to the belief that existed a couple of generations earlier. That was laughed at by science, mainstream science, I would guess. And in the years that have followed, it's getting less and less and less laughter as people go on. It is a very, very reasonable, I would say, from my perspective, probable hypothesis. You can go even beyond rare and take it a step further in that case. But anyhow, just to wrap all this up, I just want to just say that considering all this evidence about the Earth today and the stuff I gave you previously, and wrap it together, we talked about the history of the universe, the way it went from simplicity to complexity, this role the stars played so effectively to make life fit for us over time, the precise construction of the universe, those laws, those constants that are so precise, and then on Earth here, the long list of attributes that we have that are so unique to Earth here. I think any reasonable person and any reasonable scientist, if there wasn't a lot of bias, would look at it and say, there is more than just a chance of a hypothesis here, that things are very much in an ordered way. And I'd say the evidence says what we're doing is living in a purposeful universe, and we're living in a very privileged planet. And that's that idea that I talked about, the renaissance of teleology in the universe. That is, and just to cap this off, I'm going to play one more video that was produced by Michael Denton, who's done so much of this work, who I admire so much, and just let him put a cap on it.
humans live on a planet that seems optimized for scientific discovery. Our clear atmosphere and location in the galaxy enable many of the observations that have fueled modern science. Humans are not only equipped with a potential for self-reflection and scientific reasoning, they were placed on a planet that allows for that potential to be fulfilled. Far from being insignificant specks living on an insignificant planet, humans are truly a privileged species, inhabiting a home that seems to have been prepared for their benefit.
In my view, discovering the fitness of the universe, the unique fitness of the universe for carbon-based life and beings like ourselves is one of the major discoveries of 20th century science and one of the major discoveries of all time in the area of design, religion, science, and all these sorts of things. The human form is something significant in the cosmic order, and that's a scientific finding. It's implicit in astrobiologists thinking about looking for carbon-based life somewhere else and looking for oxygen on a planet. The 20th century have shown that human form is not some irrelevance, not some freak of nature. It's deeply significant. For me, I can't think of any discovery that's going to come in the 21st century which could be more significant than this, actually. It's a very significant finding.
That's Michael Denton, sort of a hero of mine. I think he's right. I think it's the most significant discovery of the 20th century. I don't think anybody will go beyond it. Okay, let's switch gears again, all right? Kevin, let's go on to the Shroud of Turin. Talk about that. And as I mentioned, I'm not going to discuss the history of the Shroud. Okay, this is strictly science and faith. So this is only about the science of the Shroud. And quite frankly, I don't really care that much about the history of the Shroud. What's important is whether the Shroud has good scientific information. If it does, then I actually don't care that much about the history. If it doesn't have good scientific information, the history wouldn't be that appealing to me. So that's the reason I can keep it very, very compact. I think it's fair to say, I'm not positive, but I think it's fair to say that the Shroud is probably the most scientifically analyzed historical artifact that exists. It's been subjected to so much stuff. It was first brought to light in a scientific sense by a photograph taken by this guy in 1898 when he took a photograph of the Shroud. Now keep in mind what a camera was like in 1898. What happened was Secondo Pio took the photographic plate, which is what he had, and looked at it, and it almost fell on the floor because what he saw on that plate was that image. That's actually a picture, an image he saw. And what he saw, that his photographic plate, which you understand is a negative, was not negative. It was positive. And it floored him. Very little was done, actually, over the next couple of decades. But in 1931, when he was still alive, he was greatly relieved that finally they allowed a second photograph, and they confirmed what he had seen, and it was true. And so at least they knew that much. And again, still, the Shroud was not released for public viewing or anything like that very often at all. It was held very quietly in conditions to preserve it. Nothing really happened until 1978, when a group of very esteemed scientists, I want to go here. I'm going to go back to the other one. When a group of these scientists were allowed to examine the Shroud. I got those pictures out of sequence. I'll come back and get them. This was called the STURP project, the Shroud of Turin Research Project. That's what it was, STURP. And it was a very distinguished, large group of scientists that did this analysis. And after looking at it very, very carefully. I'm just going to give you what their conclusions were. The conclusions were that there were no pigments, dyes, binders, or any other substances. Everybody had thought it's a painting, but nothing that's in a painting was in there. Nothing. The discoloration, in other words, the image formation, was solely from one thing, and that was the discoloration of the fibrils of the linen itself. The third thing they found was that this discoloration and the penetration of it was extremely shallow. That image that you see there is a close-up image of linen, and you could see that linen is actually made up of hundreds of little fibrils, which make up a fiber that we can see. Those fibrils are very small. They're about a couple of hundred microns across. That's millionths of a meter. The shroud image was only penetrating 5 or 10% of that depth, which is just about 10 microns or so deep, an incredibly small distance. I'll come back and summarize some of this as we go on. Give you some more of it. More findings coming up here. They found also that the coloration of the fibrils was uniform. There was no shade difference. All the coloration of the fibrils was the same. The appearance of shade was only produced from the number of fibrils that were shaded. So the depth of shade was just the number of fibrils, not the depth of them. They were all the same discoloration. Make sense? Okay? Chemically analyzing it, they found that the shade was produced by a simple degradation of cellulose. The cellulose was degraded. It had been reacted with. And it was no longer pure cellulose, but it was a degraded cellulose where the image existed. They found that there was no capillary flow anywhere in the shroud. Now, capillary flow is what you get on any kind of a substance like a linen or a sheet of paper or anything when you apply any kind of a liquid to it, right? You're going to have capillary flow. So liquid is going to move on it. There is no sign of any kind of flow of any kind of regime on the image areas. There is, however, capillary flow in the blood-stained areas. In other words, where there's blood, the blood did flow as a liquid should flow by some capillary action. Further, they found that the blood was real blood, it was type AB positive, and it had human DNA. And then the conclusions that they made was that the shroud image was that of a real human being from a scourged, crucified man, and it was not done by an artist. I'm going to go back, because I got this. I realized I put these out of order here. Yeah, I got the date wrong, too, on that one. That was a little later, so my bad there. But there was after the Stirp team did this, there was a photograph which one of the scientists took in the group and analyzed it by actually somewhat of a crude analog machine called a V8 image analyzer. What this machine did, just looking at a photograph of the shroud, not the shroud, just a photograph of the shroud, analyze the image on that photograph. And this machine has the ability to simply sort of has a mathematical formula where it translates the shade images into the appearance of topography by putting it in there. It's a brightness scale that it puts into. And when they did this, these are the images that they got from the VP8 image. And that was a great discovery, that not only was the shroud a photographic negative, it was a photographic negative that had three-dimensional information in it. even more amazing. Now I got to catch up and get back to where I'm going. Okay. So that's the story of the scientific information about the shroud. There were some skeptics, and there was a lot of kickback on it, none of which really stuck. All of it was analyzed, and none of it had a lot. The biggest one that you probably heard about was the carbon-14 dating. That's the one that really hung in for a long time. In 1988, a sample of it was given to a few labs in England and the United States, and one other country, I think, and they ran tests on it, and they dated it as being 1260 to 1370, or something like that, I think the date was. And the word went out, it's a fake. And everybody said, the shroud is a fake. Well, it turns out that there was such a litany of errors, problems, protocols, and mistakes made in those tests that it was completely discredited, all the work that was done. The sampling technique was horrific. They got bad samples, they got other materials in it. They didn't follow the protocols. They didn't do anything right. And so that is just discredited. Now, there hasn't been another carbon-14 dating done since then. And one could be done, but simply hasn't been done. Not for any reason, it just hasn't been done. One other person said there was iron oxide in there that was used for part of the painting. That was easily discredited. One researcher disclaimed the veracity of the blood sample. That was discredited easily too. In the end, there really haven't been any lasting criticisms of all those conclusions that I just gave to you. And it's just out there right now. And it's just very, very interesting. Then, of course, what you've got from the gospel accounts, as far as taking that now beyond the realm of science into the realm of the Gospels, is all these other things, which is beyond science, but which are present from the gospel accounts, all of which are consistent in the shroud with the Gospels. Science can't comment on this, but a reasonable person can look at them and draw their conclusions from it. And again, I'm just sticking to science right here. The consistency is very high between them. And finally, one more thing about the shroud I want to say. And I'm just sticking with science here, okay? Just sticking with it. It's a very interesting and almost completely unrelated work that was done much more recently. If you have an inquiring mind, I think about this, you got to ask a question. How did the image get there, right? Don't you want to know? I mean, it's the real, even a supernatural cause in the material world has a material manifestation, right? The image is a material manifestation. What caused it? Was it just completely supernatural, or was it something caused that in the material world that then caused this? Jesus' body, or speaking scientifically, the dead man's body was dead and came back to life, or produced, the dead man's body gave this energy that produced an image, did something to produce an image. How did that happen? It is a good image of the body. You had to get from the body somehow. And that's where this work comes in that I really like. And the work was done with, remember I talked about the electromagnetic spectrum? We're going to go back to that too, because they did some work with what's called far ultraviolet or vacuum ultraviolet light, illuminating fibers of linens, and they were able to produce something like this, which was done by illuminating with ultraviolet light linen fibers, and they were able to get almost exactly the same coloration as the color qualities on the shroud. The very same, almost an exact match on the color and the degree of penetration. And for this, they use what's called vacuum ultraviolet radiation. And to go back to our graphic before, I'll just show you this. Again, just to stick with science. This is a very small portion of the electromagnetic spectrum. Here's visible light. Here's the radio waves down over here. Okay, here's the more powerful stuff, but we're just doing a tiny section, okay? And the frequencies they used was first this one and that one. This was the first one they did in the test. It didn't do too well. This is the one that they used to produce the color you saw, and it was over here. And you'll notice we're in the portion of the spectrum where you don't get a lot of transmission, right? You get a lot of absorption of energy, right? There's a lot of absorption here, a lot of transmission here. All the radio waves are transmitted here. Light's transmitted very highly. You get over here into the ultraviolet, and we're down right here, right? Very little transmission, high absorption by the atmosphere. So the interesting thing here is, well, let me just show you one more thing before I tell you. Let's go to this. They actually took a photograph of the shroud, used a scanning scanning laser with that energy level, and scanned an image of the photograph, and was able to produce that image by using this technique. Now, this is just a photographic image, but they did it with that frequency and produced an image which is amazingly like the image on the shroud. All I'm saying is it's close. It's just something that could be done. The thing that intrigues me is that this is a hypothesis, but who can describe or even talk about a supernatural cause of the resurrection? No one. No one. It's beyond our scope. But could we just speculate that whatever it does, something had to be actuated, something had to be the tool? And all this is saying is, here again is energy. One of the basic things, somehow that energy was there that resurrected the dead life and produced it. The interesting thing is that if you look at the image right here, because of a negative, the parts that show up the most are the parts closest to the shroud. That would be like the nose, the hands. Those have the most image development. And those are the ones that are closest, right? And the ones that are furthest away have less image development. And the thesis would be that the air between them is absorbing some of the radiation and that you could produce it. Now, it's just for fun, but I think it's an amazing piece of science that who knows where it could go. Okay. Let's move on. Last thing, and I think I'll take a want to darn it. But I will go on and talk about near-death experiences. The thing about near-death experiences that's so interesting is that it's such a challenge to the materialist science that we have today. And it challenges it on two levels. First, it challenges on the level of the idea that consciousness itself is nothing other than brain activity, that it's strictly a material phenomenon. And of course, the other thing it obviously challenges is that there is nothing beyond the physical, there is no life after the physical. But I'm just going to play a video here from a gentleman by the name of Bruce Grayson, who's been doing this for 40 years, and who is as a young doctor had a patient who had a near-death experience and saw something that he couldn't explain. He had been in the cafeteria eating lunch and spilled spaghetti sauce in his tie and was talking to a girl who had a near-death experience, his friend, and went back the next day to talk to the girl in the operating room, and she asked him about that, that stain on his tie, which he showed the other girl, and it got him going. And from that day on, he kept investigating this phenomenon, and he did it for the rest of his career. And I'll let him talk about the near-death experience.
I'm Bruce Grayson. I'm a professor emeritus of psychiatry and neurobehavioral sciences at the University of Virginia Medical School. And I've recently come out with a book called After. A doctor explores what near-death experiences reveal about life and beyond. Near-death experiences are profound, subjective experiences that many people have when they come close to death, or sometimes when they are in fact pronounced dead. And they include such difficult-to-explain phenomena as a sense of leaving the physical body, reviewing one's entire life, encountering some other entities that aren't physically present, and at some point coming to a point of no return beyond which they can't continue and still come back to life. When they return, they often are profoundly changed by this experience. When I first started looking into near-death experiences back in the late 1970s, I assumed that there would be some physiological explanation for that. What I found over the decades was that the various simple explanations we could think of, like lack of oxygen, drugs given to the people, and so forth, don't pan out. The data do not support them. And furthermore, the phenomena of NDEs, of near-death experiences, seem to defy a simple materialistic explanation. When we first started presenting this material in medical conferences, there would be a polite silence in the audience. And now, in the 21st century, when we do this, it's rare that doctors don't stand up in the audience and say, "Let me share my experience with you." So it's pretty well accepted now that these are common experiences that people have all the time and that have profound effects. There's still, of course, a lot of controversy about what causes them, but not about the fact that they exist and are fairly common. I never expected to spend so much time looking into near-death experiences. I thought at first it was just a strange anomaly. I'd spend a few years looking at them, find the physiological explanation, and put it behind me. I collected about 1,000 cases that people had sent to me about their own near-death experiences. Quickly realized that the stories I was getting from people who volunteered their stories to me were the same as the ones from people I interviewed in the hospital. We studied the physiological events around the near-death experience, psychological traits of the experiencers, and so forth, trying to find some logical explanation for these events. Most of us are taught that the mind is what the brain does, that all our thoughts, our feelings, our perceptions, our memories are all created by the brain. However, that's not the whole story, and we have hundreds and hundreds of experiences that occur during a cardiac arrest or deep anesthesia when we know the brain is not capable of functioning well enough to create complex thoughts and feelings and memories. Most near-death experiencers say that in the near-death experience, their senses were incredibly heightened, and they often report hearing sounds they'd never heard on Earth and seeing colors that they'd never seen before. And when they come back, they don't know how to describe these things because there aren't words for them to describe them. One person said to me, it's like trying to draw an odor with a crayon. But they talk about their senses being so much more vivid in the NDE, and that gives the experience a sense of being more real than this world is.
There's an interesting correlation between NDEs and miracles. They both share the characteristic that they're incredibly underreported and probably much more common. For NDEs, the number that have actually been reported in studies are in the tens of thousands that have started since that. Some of you probably remember Raymond Moody, the book Life After Life. He's the one who got it started. That book was published in 1975. Dr. Grayson, one of the real pioneers, had his experience shortly after that. And he's in a group now at the University of Virginia of about a dozen professionals, all PhDs, that now study these kind of things called parapsychological events. Gallup, years ago, I don't know where they got that number, quite honestly. But like I said, there's a real parallel between near-death experiences and miracles. There's a gentleman by the name of Craig Keener, whom my mentor, Bishop Barron, has written a foreword to in his book and commented on a book called Miracles. Which catalogs exhaustively the number of miracles that are happening all the time. that people just don't report them. People feel odd reporting them. I saw a miracle. Has anybody else seen a miracle? I had someone come up to me and report a miracle that they didn't want to report. But my miracle was my mother. She had I went in the early 1980s to in a parish I was in to a healing service. We had a priest who had a charism for that. Once a quarter, he said a healing mass, and who were living in Florida at the time came up and joined me, and I asked them if they would go, and they said, okay. They weren't particularly interested. They're not religious people, but they decided to go with me, and my mom had injured her ankle. She had sprained it severely before she came. It was swollen like that, and she hobbled around, but she was a trooper. Anyhow, at the point in the service where we just went up and just had the priest lay his hands and just pray for us, he just did that almost for everybody who was in the congregation, and I went ahead of my mother and my father, and I didn't think much of it, quite honestly. I just said a prayer, and he prayed over me. I went back in the pew. A little bit later, my mom came back and sat next to me, and I felt a tap on my shoulder, and she said, healed. Perfectly normal. Was that a big deal? No. But what was it? It was just one of those things that happened, huh? I had another person, I won't go into it, tell me a story of a wonderful miracle that they experienced. And anyhow, those are much more reported. I said, I think I've gone right to the time limit again and done it, so I don't think we have any time left. If you want to stick around. Yeah, if you want to stick around, I hope I got a little earlier, but we could take some questions if you like.
Yeah. Okay, we'll do some Q&A afterwards if you want to stick around, if you have anything from the 4 sessions. But I want to thank Bob for all the time and energy he puts together. It's beautiful when each one of us uses the time and the talents that God's given us. And Bob's been an active part of our parish for a long time, involved in the adult education committee, and brought so many wonderful things. And Bishop Barron is one of our shared loves. And we're challenged to look for, the good, the true, and the beautiful right now especially. So if this kind of sparks something, I think we're going to be able to put all these recordings out on the website and maybe give you a few resources, some of the favorites, and maybe link you there and give you a start if you want to continue on this conversation, because it's not just for your own edification and knowledge, but it's for conversation, and then, of course, it's to share with the world. It's to share with the world. And it's a really beautiful thing when you can recognize the link between reason and faith, and with science falling underneath reason, because it's a gift from God for us to be able to reason, to look for solutions. But our faith is not just a hopeful thing. It's based on the good reason with beautiful expectant confidence that something good, true, or beautiful exists because of God. So it's not a jump or this or the other. So thank you so much for your talk, Bob, and your time. If you want to stick afterwards for Q&A, please do. But I want to invite you also to our summer series on Wednesday nights. It'll be kind of a slightly off but somewhat related topic by Dr. Sri, a series on Formed, Who Am I to Judge, on moral relativism, and basically trying to understand and kind of tackle those tough conversations we might have with others based on, what's my truth and what's your truth, and it's okay for me, and whatever you believe is okay for you, but that's not quite the Catholic view. So thank you so much. Let's give a round of applause to Bob.